In IEEE floating point presentations, we have a special value that is for a single precision case. If the exponent is 255, remember exponent has 8 bit, so if we have all ones in 8 bits, the value in decimal is 255. So if exponent has all ones, then depending on significand, if significand is 0, that is a infinity value is represented by that. So depending on the sign bit, it's a positive or negative. Infinity is when exponent has all ones with the significand 0. But if a significand is not 0, then the value is called a not number ones. So if you have some Java experience, depending on the computing the result, you may get infinity or not a number. So that is stored in IEEE single precision format according to that. In double precision, since exponent has 11 bit, if you have all ones for 11 bits, equivalent decimal value is 2047. So using this one is so either case single precision or double precision, either case exponent has all ones, then depending on significant, then it's a negative infinity or not a number is represented in floating point representation. So another observation is that IEEE 754 floating point allows two representation of a zero. So you have a bit because we have a sign bit separated. So you have a positive 0 and negative 0. And then because of that, when you write the programs in any language, do not compare 4 0. So if you have a result by computation, it might be end up negative 0 in the floating point representation. But if you compare with this one positive 0, then this is false, not equal to, and so on. So you should never ever compare directly with the floating point values. Actually, this is not just for zeros. So any numbers, don't use equal sign for direct comparison in floating point, but instead find the difference between two floating point numbers and then take absolute, and then if the absolute is small enough, then consider they are equal. That's how you should do that in programming part. Then what is this value? How do you find it? Depending on your application. If you represent this value as a money, and then whole part is dollar, and then you have a cents after that, then 0.001 should be small enough to see if two money values are equal or not. So depending on your application, you could find what is small enough to tell those two values are equal. So another thing you need to remember is that no matter how many bits we use in floating point representation, our model is a finite. It means that we can represent only finite number of values. So floating point is to represent the real number in math. It's a real number in math. So you have a negative infinity, positive infinity, between how many numbers you have in real number. Even between 0 and 1, you have a infinite number of values in real number. So, but a floating point representation, we have a finite. So always there is a limit. So real number system is infinite, but floating point is a finite. Because of that, there is some error. So if you use double precision, the errors are reduced compared to single precision though. So floating point could be overflow or underflow because it's a finite. So overflow means the number is too big. So exponent, you have 8 bit in single precision, but if you have a too big number, then exponent with 8 bit may not be sufficient. That is overflow, significant at the same way. Underflow, the value may be too small to represent. It's a negative 10 to the negative 44,532. So this kind of a small value cannot be represented. That is a underflow situation.